My name is Dr. Ryan Conversano. I am an aerospace engineer working as a rocket propulsion scientist for a leading U.S. spacecraft development and flight operations firm. In this role, I help to create the future of spacecraft propulsion. As a result, I tend to judge the merit of machines and objects from a more technical perspective. Today, I am here at the Thought Leadership Center to look at the McLaren 720S and explore the science behind this amazing car, with a nod towards Newton's second law of motion, which states that force equals mass times acceleration. If we rearrange this equation, we find that acceleration equals force divided by mass. This equation of acceleration will be the focus of our analysis. Ever since I first saw the 720S in person, I realized how aerodynamically interesting and from some angles unusual the design is. It's in this isolated setting that those aerodynamic qualities become even more obvious. It's these qualities that lead us to the first part of our equation, acceleration. A car has to use the air flowing over its body as an ally, as a tool. I may have a PhD in aerospace engineering, but anyone can see how much aerodynamic design went into this car. The 720S features smooth flowing lines with no sharp angles or large intake vents. This is a testament to McLaren engineers and how much effort they put towards enhancing and optimizing aerodynamic efficiency, enabling this car to achieve an impressive 212 miles an hour. Air coming to the nose of the car is split both above and below the vehicle. Air flowing downwards encounters a high-efficiency splitter, which provides downforce to enhance cornering and grip. Air flowing behind the headlight here and below provide cooling to a low-temperature radiator, before flowing out of this vent to provide laminar airflow along the side of the vehicle. Air flowing over the car encounters these hood air vents, which guide air through into the windshield area, over the A-pillar, and into the channel in between the door's inner and outer skin. This houses the high-temperature radiators, which require a significant amount of cooling when the car is being driven hard. In between the inner and outer skin, there is a small buttress that's actually in the shape of an airfoil to accelerate air down and into the channel. The rear of the 720S sits lower than any previous Super Series model, the chassis aggressively tapering from the glass teardrop of the cabin to meet this full-width rear wing. It's very similar in profile to that of an airfoil. With the wing stowed, it's cleanly integrated with the body panel to offer minimized drag. The 720S's active aerodynamics controls the wing angle when accelerating, creating maximum downforce and high-speed stability with as little drag as possible. This is similar to the deployable aerostructures of an aircraft. They alter the airflow over the vehicle to generate optimum performance. Hard deceleration from high speed causes the rear wing to deploy fully in just half a second, placing it near vertical to direct the oncoming airflow upwards. This increases rear-end downforce to shift the dynamic balance of the car rearward by 20%. This cancels the natural nosedive tendency of the vehicle when braking from high speed, as well as enabling a complete stop from 124 miles an hour in just 4.6 seconds. The second part of our equation is force. In my current role, I work on bleeding-edge spacecraft electric propulsion technologies, also known as EP. These devices use electrical power to ionize and accelerate gas particles, creating a plasma jet that pushes you through space. In operation, these devices look very similar to the rings above me. These devices tend to be very efficient and have been flying in space for over half a century. The real question, however, is how much power are we talking about? One of the most high-powered electric thrusters ever to fly in space produced roughly 30 kilowatts of propulsive power, which is equivalent to 40 mechanical horsepower. That's less than 6% of the 710 brake horsepower produced by this 720S. Even a manned mission to Mars requires on the order of 500 kilowatts, 670 mechanical horsepower. That's still less than this McLaren. From this perspective, New Age spacecraft propulsion might not sound too impressive. However, since these high-tech electric thrusters operate in the vacuum of space instead of inside the Earth's dense atmosphere, EP spacecraft have the potential to reach speeds far beyond any car, tens or even hundreds of thousands of miles an hour, possibly more, unlocking the potential to travel farther and faster than anything man-made has ever gone before. On the other hand, even the most advanced electric thrusters produce only a few pounds of force, several orders of magnitude less than the force experienced by the driver of a 720S at full throttle. The final part of our equation is mass. Aerospace engineering is frequently about achieving the lightest design possible, cutting down to only what you need to enhance total system efficiency. Advanced materials such as carbon fiber, titanium, and magnesium are often used in both aircraft and spacecraft to achieve high-strength, low-weight structures. A similar philosophy is an obvious part of how McLaren designs its cars. Following in the automaker's tradition, the 720S surrounds the driver with a carbon fiber tub, providing a frame that's incredibly strong, rigid, and light. I'm told that the newest carbon tub found in the 720S, called Monocage 2, weighs just 102 kilograms, an impressively low weight for a structural chassis. While using carbon fiber for the tub has multiple dynamic benefits, its inherent torsional rigidity enables the integration of these ultra-thin pillars at each corner of the cabin. This creates a beautiful glass-filled driving environment that is unlike any other supercar I've seen. As a trained pilot, I can honestly say that the view outside of this vehicle is better than most of the aircraft I've flown. The driver has a nearly unobstructed view of the world around them, whether it's the stars in the sky or the apex of the next corner. The McLaren 720S is at the pinnacle of supercar science and engineering. While both beautiful and unique, the fundamental principle of form follows function rings true throughout its design. McLaren has pushed the limits of consumer road car performance. Aerodynamics that enable savage acceleration, a power plant capable of mind-blowing forward thrust, and a super light total mass. These three components of our equation of acceleration coalesce to make the 720S a very impressive vehicle. Indeed, a true marvel of modern automotive engineering.